Hello everyone, welcome back to another episode of Studysmart. In today's video, we are going to be talking about the nth order linear ordinary differential equation with a constant coefficient. Alright, so the nth order linear ordinary differential equation is an equation that is expressed in this form. So the nth order linear ordinary differential equation is given by the expression dny over dx to power n plus a1 dn minus 1 of y over dxn minus 1 plus a2 dn minus 1, then it continues in that form to plus an of y equal to f of x. So if we call this equation 1, so where you can say where a1 is a1, a2 down to our an is called an arbitrary constant. This is an arbitrary constant. So from our equation 1, if we equate f of x to be equal to 0, it means that if I let f of x here to be equal to 0, then my equation 1, which is this expression, transforms to the form of dny over dxn plus a1 of dn minus 1 of y over dxn minus 1 plus a2 dn minus 1 of y over dxn minus 1 plus an of y equal to 0. Alright, so we can call this equation 2. So from our topic, ordinary differential equation with constant coefficient. Alright, so in this ordinary differential equation, we have both the homogeneous part and the non-homogeneous part. Alright, so from equation 2, which we are going to be pondering on, it's called the homogeneous part of this differential equation. So we can say that equation 2 is the homogeneous equation. Alright, is the homogeneous equation, which we are going to be talking about in this video. Then maybe in our subsequent videos, we'll drill on the non-homogeneous part of the differential equation. Alright, so equation 2 is called the homogeneous equation. It's called the homogeneous equation. Alright, so there are many methods, different methods of solving equations that are homogeneous. To look for the methods of solutions of a homogeneous equation, we have to look for what we call, let's say, methods of solution. Methods of solution. Methods of solution. We are going to look for in the equation what we call the auxiliary equation or the characteristics equation or the general solution. Alright, so the number one, we are going to look for what we call the auxiliary equation. This is the auxiliary equation. Alright, we look for the auxiliary equation, or you can call it the characteristics equation. Or the characteristics equation. Then after looking for the auxiliary equation, we'll go further to look for what we call the particular solution. So this is a particular solution. Particular solution. Alright. So there are some conditions that governs this particular solution. Before you can be able to look for the particular solution in an ODE, you must be given some boundary conditions. You must be given some boundary conditions. For example, you can be given an ODE, a homogeneous equation, and then you will be given a boundary condition of, let me say, y of 0 equal to 4, and then y prime of 0 equal to 2. These are called boundary conditions. So without these boundary conditions, you cannot obtain the particular solution of the ODE. So you need the auxiliary equation to substitute the boundary conditions in order for you to get the particular solution. So as we progress in the video, we are going to be drilling on examples that will clarify us more on this topic. All right. I'm going to be telling you some basic processes you follow in order of solving the homogeneous part of an ODE. In order of solving the homogeneous part of an ODE. Firstly, for you to solve the homogeneous part of an ordinary differential equation, you need some basic rules to follow. So I will give you some basic rules you will have to follow. First, you are going to look for what we call the auxiliary solution, which I give you earlier, methods of solution. So you are going to form an auxiliary equation. So the first rule, you are going to form an auxiliary equation. You form an auxiliary equation. You form an auxiliary equation of the form f of m equal to 0. All right, f of m equal to 0. And this auxiliary equation is always expressed in the form of y equal to exponential mx. It's always expressed in the form of exponential mx. Then after you've looked for the auxiliary equation, you go further to look for the roots of m. You look for the roots of the auxiliary equation. So you find the roots of the auxiliary equation. All right, the roots there I mean is maybe this is the root here, this m. So you are going to look for the basic roots. M1 equal to A, M2 equal to, let me say, B, and then M3 equal to C. All right, all these alphabets you are seeing here, A, B, C, they can be any number. All right, they can be any number. While M1, M2, and M3 are the roots. So this M1 is equal to a certain number, M2 is equal to a certain number, while M3 is equal to a certain number. Then the last rule I'm going to give to you will be determined by the kind of roots you are getting from the auxiliary equation. All right, so the kind of roots you get from this auxiliary equation will determine the next step you follow and the next method you are going to use. So I will just leave a write-up here, then and I will say the kind of roots. The roots here determines the next procedure. All right, why I say this is because the roots you will get from an auxiliary equation can either be a real and distinct root, it can either be a real and repeated root, and it can also be a complex and imaginary root. So I'm going to give you some basic rules also, maybe some guidelines you follow when it comes to different roots in an auxiliary. So I've told you that you form an equation, and I gave you a basic expression for an auxiliary, a basic expression for a homogeneous equation. For example of that, let's say example of a homogeneous equation. If I have y prime, if I have y prime prime, which represents the square y over dx, and I have plus y prime, and I have plus 3 equal to 0. This is called a homogeneous equation because it is equal to 0. Yeah, from the initial expression I gave you, from the beginning of the video, I gave you a certain expression, and I said, if assuming f of x is equal to 0, that the expression is called a homogeneous equation. This is a typical example of that. So you can just put a label here and then call this a homogeneous equation. All right, for easy clarification. All right, so let's go further by knowing some basic guidelines you will use in order of solving this homogeneous differential equation. All right, so for first rule or first process, when we have a real and distinct root, for a real and distinct root, for a real and distinct root. Alright, so if you are forming an auxiliary equation for a real and distinct root, it is going to be equal to y equal to c1 exponential mx plus c2 exponential, this is m1 and this is m2x, and it continues in that form to cn exponential mnx, which means that my c1, c2 and c3 will be the values I will look for in order for me to look for or maybe form a particular solution. Alright, a particular solution. But for a real and distinct root, this is the formula you are going to use after getting the roots. All you just need to do is not hard. What you are going to do is not hard. What you will do, you are going to form an equation, like I said earlier. You form an auxiliary equation from a given expression. Then you are going to look for the roots m1, m2, and then maybe m3 to any certain number of m you've gotten. Then after you've looked for the roots, all you just need to do is to take the numbers in that root and then you substitute them back to this expression. It's only applicable when the root is real and distinct. That's when you are going to use this expression. It has another expression for a real and repeated root. What I mean by distinct is, I mean that the roots are not repeating. Alright. For example, if I have m1 equal to 2 and I have m2 equal to 3 and then I have maybe 3 equal to 1. Alright, so this is a real and distinct root. It is distinct because the numbers are not repeating. That's why it is called a distinct root. It is a real and a distinct root. So this is the first condition. So I'm going to give you again the second condition. Alright, the second condition, since we've gotten the real and distinct roots, the condition that governs it, if I get a real and distinct root, this is what I will use in order for me to be able to substitute the value of my m1, m2, and then maybe to any number of m you've gotten. Alright, so for a real and repeated root, for a real and repeated root, is no longer in this form because the numbers are now repeating. So I'm going to have y to be equal to, I have c1 exponential m1x. The second one will add an x to it, so I'll have c2x exponential m2x, then c3x squared exponential m3x, and it continues in that form to cnxn exponential mnx. Alright, so I'll give a typical example of this. So if I have m1 to be equal to 2, and I have m2 to be equal to 2, and I have m3 to be equal to 1. Alright, so if you observe very well, 2 and 2, they are recurring. So this is a repeated root. Alright, this is a repeated root. So if you have such cases like this is kind of expression you are going to use. This is the kind of expression you are going to use. What if I have a complex and imaginary root as my root? What I mean by that is, maybe what I mean by complex and imaginary root is that, for example, if I have m1 to be equal to a plus bi, alright, this is a complex and imaginary root because of this I. This is an imaginary root because of this I. So take note of that. Alright, so we are going to be taking this third condition, which is a third condition for a complex and imaginary roots. For a complex and imaginary roots. Alright, so for a complex and imaginary roots, this condition no longer carries because it is having a complex root and as well an imaginary root on it. So if I have a complex root as my root, what kind of expression or what kind of condition am I supposed to follow? I will have my y to be equal to, I will have my c1, then I'm going to have my cos bx, I will have my plus c2, I will have sine bx, and I'm going to have exponential mx. All right. So this is the rule here. If I have a complex and imaginary root, this is the condition I'm going to follow. This is the condition I'm going to follow. There are some cases where the roots, the imaginary roots, have to reoccur. For example, let me just give an example of this. Let me say you have m1 to be equal to 2 plus 4i. I have m2 to be equal to 3 plus 6i. Right. So this is a typical example of what I mean by imaginary roots, because it is having I. What if the roots are reoccurring? These roots, what if they are reoccurring? Okay, let me just change here to a 0. Let me just put 4i and then 6i. What if 4i and 6i are reoccurring? Will you still use the same condition? You will use the same condition, it's true, but if you check the real and distinct and then the real and repeated, there is just something that is changing on it. If you check very well, you see x here, you see x square here, and then you see xn here. Then if you check here, you are seeing no x, sorry. That is because in this case, no root is repeating, but in this case, roots are repeating. What if they are imaginary and the roots are repeating? What will you do? So let me say condition 4. For repeated complex roots and imaginary roots. So repeated complex roots, complex and imaginary roots. So the idea here is very simple. Look at the other one. We have this first one, there was no x. The second one, there was x. And if you check very well, there is something so spectacular about the x. It was increasing by the exponent from 1 to 2, then maybe to any other power, right? So that's how this one will be too. So if you check very well here, there was no x here, all right, but we will have x. But because the numbers, the imaginary numbers are repeating, I will have y to be equal to c1 of x, all right? Then I have my cos bx plus c2 of x. I have my sine bx. Then outside, I have my exponential mx. All right, so these are the conditions. And then we are going to be taking some simple examples in order for us to easily identify or comprehend what I'm talking about. All right, so let's just take a very quick example. If I have an example, let me see an example here, then solve or find or solve the homogeneous equation. The homogeneous equation, and I have the expression of y prime prime plus 3y prime plus 2y equal to 0 at condition where y of 0 is equal to 0 and then y prime of 0 is equal to 4. All right, so if you can recall from the initial rules and conditions I gave you, I told you that from this point now, you know that you are going to end at a particular solution because boundary conditions have already been given. Assuming you are not given the boundary conditions, you only form the auxiliary equation without the particular solution. All right, so let's drop a solution here. All right, so from our basic knowledge of calculus, we know that y prime prime is also the same thing as the square y over dx squared. So it's also the same thing. So let's just bring down our expression down. So I'm going to have y prime prime plus 3y prime plus 2y equal to 0. So I'm going to deduce this thing or disintegrate it into the minimum. So we are going to comprehend what I'm talking about. So from our initial knowledge or idea of calculus, we know that the y prime prime means the square y over dx. So I'm going to have here, deducing this, I will have the square y over the x squared. All right, so that's for this. I'm having plus 3. And if the square y is the square y over dx squared is this, it means that y prime is dy over dx. So this is dy over dx, then plus what of y? Y is just y, so I have 2y equal to 0. Right, so this expression means the same thing with this. And if you can recall from the rules I told you in solving a homogeneous differential equation, I told you that when you've gotten the homogeneous differential equation, which is this, in order for you to solve it, you first form what we call an auxiliary equation. And I gave an expression of the auxiliary equation. I said that for an auxiliary equation, y is equal to exponential mx. All right. So where this m is the root, this m is the root. So I'm going to use this expression. I'm going to use this expression to solve for this. The idea there is very simple. In forming this auxiliary equation, the highest power here is 2. The highest power is 2. And the lowest power here is 1. In talking about the differences. Okay, 0. The lowest power here is 0. So it deduces from 2 down to 0. It deduces from 2 down to 0. Alright. So we are going to solve this. The idea here is very simple. I'm going to differentiate this. I'm going to differentiate it because the highest power here is 2. So I'm going to differentiate this thing twice. If assuming I have the highest power of 3 here, I'm going to differentiate this expression 3 times. If I have it to the power 6, I'm going to differentiate it 6 times. All right, so this is the square y over the x squared. So this is y with respect to this. So in this case, y is a function of x. Y is a function of x. So I'm going to look for dy over dx. So dy dx is going to give me, from this expression, the idea is very simple in differentiating an exponential function. The cheat here is that you pick up this constant here, you bring it to the front, and then multiply it by everything you have here. So I'm going to have m. Now multiply m with everything I have here. So I'm going to have exponential mx. So this is my dy over dx. What if I'm going to differentiate that thing again? I'm still going to move this m, now multiply by everything here. So the square y, so the square y over the x squared is going to give me m squared, then exponential mx. So if you check very well, I know my value of y, I know my value of dy dx, and I know my value of the square y dx. So I cannot substitute all these things back to this particular expression for me to solve this thing homogeneously. So I'm going to solve that thing. So my d square y over dx squared, that's my y prime prime, is this, which is m squared exponential mx. So I will come back here and I will write m squared exponential mx. I have a plus sign, I have plus, and I have my 3. I have 3. What's my dy dx? M exponential mx. This is m exponential mx plus, I have 2, and I have y here to be exponential mx. So this is exponential mx equal to 0. So we've succeeded in deducing this thing to this form and then back to this form by substituting it with the expression for the auxiliary expression and its differentials, which is this. All right. So if you check very well from this new expression we had, you will see that exponential mx is common. So I'm going to factor out exponential mx. So I'm going to have exponential mx into m squared plus 3m plus 2 equal to 0. So if you check very well here, inside this bracket, I have m squared 3m plus 2. And this is a quadratic equation. This is a polynomial. So I'm going to solve this thing quadratically. All right. So I can only solve this thing quadratically provided that exponential mx is not equal to 0. Because if exponential mx is equal to 0, the whole expression here automatically becomes 0. And it will not make sense. So the major aim for us is to look for the roots of the auxiliary equation so that we can be able to the quadratic equation so that we can be able to form the auxiliary equation. All right. So provided that exponential mx is not equal to 0, so I'm going to pull out m squared plus 3m plus 2. So I will have m squared plus 3m plus 2. I will have equal to 0. So from here I can solve this thing quadratically now. So the major cheat we do in quadratic equation, we are going to look for two roots such that when we multiply them, it will give us the constant here. When we multiply these two roots, it will give us this 2. And then when we add them, it will give us 3. So if you check very well, 2 plus 2 and plus 1 can go. Don't forget you are considering the signs in front of each values. So if I say 2 times 2 plus 2 times 1 is giving me plus 2. If I say plus 2 plus 1 give me plus 3. So it means that I've gotten the roots of this equation. So I can transform this equation to be m plus 1 and m plus 2 equal to 0. All right. So this is my new expression. So don't forget, in this kind of expression, if you have xy to be equal to 0, let me use the case of AB, a plus 1 and then a plus b equal to 0. It automatically means that this 0 is being distributed to the two expression here. It means that a plus 1 is equal to 0 or a plus b is equal to 0. So we are going to use this idea in this place. So because I know that m plus 1, m plus 2 is equal to 0, it means that m plus 1 here is equal to 0 and m plus 2 is equal to 0. So I'm going to look for the value of m. So I can call here m1 and call here m2. All right. So the value for my m1 is m1 equal to minus 1. And for my m2, I have m2 to be equal to minus 2. So I've gotten the roots of that particular expression, the root of this quadratic equation. I've gotten the root, which is minus 1 and 2. So from the conditions I gave you, I told you that there are expressions for when the roots are real and distinct. So if you check very well, this rule is a real and distinct root because it is not repeating. Assuming I have m3 equal to maybe minus 2. All right, so this is no longer a real and distinct root, but rather a real and repeated root because it has minus 2 here and also has minus 2 here. So I can use the second condition I give. So in this case, because the roots are real and distinct, I am going to use the first case I gave you where I said that for a distinct root. So you can specify that by saying that for a real and distinct root, y will be equal to c1 exponential m1x plus c2 exponential m2x, because we have only two roots here. Assuming I have up to 3 roots, then I will extend this thing up to 3. All right, so I'm going to have y equal to C1 exponential. The value of my N1 here is minus 1. So this will be minus x plus C2 exponential. The value for M2 here is minus 2. So I will have minus 2x. All right, so this becomes the answer to the first case. All right, assuming this boundary condition was not given, you can end your solution here. All right, you can end it here. But provided that this boundary condition is given, this is what we just call the auxiliary equation. This is the auxiliary equation. All right, this is the auxiliary equation. So with this auxiliary equation, you can now proceed to look for the particular solution. So the auxiliary equation is this. All right, so let us go further by looking for the particular solution. So for particular solution, we can say recall the auxiliary equation. Recall the auxiliary equation. And what's our auxiliary equation? This. So y is equal to C1 exponential minus x plus C2 exponential minus 2x. So from this point, provided that we are given a boundary condition, so we are going to introducing boundary conditions now. Boundary conditions. And what are these boundary conditions? I have okay, let us just call this equation 1. All right, so I will have the first I was given two boundary conditions. The first one was y of 0. This means y of x equal to y of 0 equal to 0. It means that this 0 inside is for x. All right, this 0 inside is for x. Assuming the function you have was y to be the function of t, then here will no longer be x, it becomes a t. All right, so the t has this 0, y has this 0. All right, so we are going to use this sheet to follow it up. So I have my boundary condition for first case. So first case, I have y of 0 equal to 0. So I'm going to substitute this into equation 1, which is the auxiliary equation. So if I substitute this into equation 1, which is the auxiliary equation, I'm going to have y here is equal to 0, x here is equal to 0. So I'm going to have 0 equal to C1 exponential minus 0 plus C2 exponential minus 2 times 0. Right, so this is my new expression. So 0 will be equal to, this is 0. So from our law of indices, okay, this is C1 exponential minus 0, which is 0, plus C2 exponential 0. Right, so this is the new expression I have. All right, so this is the new expression I have. So from the idea of indices, from our law of indices, we know that any number raised to the power of 0 is 1, apart from 0 to power 0. So if I have 1 raised to power 0 is 1, apart from 0 to power 0. Because if you put 0 to power 0 in your casio or any calculator, it will give you a math error. To give you a math error. So the law of indices states that any number, anything raised to power of 0 is 1. So it means that this is 1 because it is raised to power 0, and this is 1 because it is raised to power 0. So my new expression here becomes y C1 plus C2 equal to 0. So I can call this, since I have equation 1, I can call this equation 2. So I can call this equation 2. So this is my new expression. So the second boundary condition was y prime of 0 equal to 4. So for case 2, y prime of 0 equal to 4. It means that my y prime here is 4 and my x here is 0. But how do I get my y prime? Where do I get my y prime from? I'm going to get my y prime from the auxiliary equation. It means that I'm going to differentiate the auxiliary equation once. All right. There are some conditions you'll be given up to 3 boundary conditions, y prime, and then you have y prime prime, maybe y prime prime, as the case may be. All right. So I'm going to differentiate equation 1 in order for me to obtain y prime. So differentiating equation 1. So if I differentiate equation 1, that turns into y prime, all right, equal to, just like I said earlier, if you are differentiating exponential mx, what you do, this is like a constant, all right, this is like a constant. I'm going to pull up this constant from this place. I'll bring it to the front and I'll multiply it by everything here. So I'm going to use that idea in differentiating this. So this is y prime equal to the coefficient of x here is 1. So I'm going to pull up minus 1 because the 1 is carrying a minus sign. So I'll pull out minus 1 to this point here. I'll bring it to the front and I'll multiply it by the whole of this. So if I pull up minus 1 there, I'm going to have minus c1, and I'll have exponential minus x. Alright, so for c2, this is a minus. So minus 2 times the whole of this expression here turns into minus. I'll have minus 2c2 exponential minus 2x. All right, so from this second condition now, so we can call this, okay, let's leave it. So from this point, we've gotten y prime, and the second boundary conditions gave us y prime to be 4, x to be 0. So I'm going to substitute that second boundary condition, which is this, into the differential of this auxiliary equation that we've gotten. So y prime here is 4. This is minus c1 exponential, this is 0, minus 2c2 exponential. If I put 0 here, I'm getting 0. All right. So this is 4 equal to minus c1 minus 2c2. All right. So this is equation 3. So let's call this equation 3. All right. So the major aim while we are doing this is for us to get the values of C1 and C2. So let's write our root somewhere so we don't forget it. M1 was minus 1. All right. M2 was minus 2. So let's just drop it here so we don't forget it. So we are going to solve equation 2 and equation 3 simultaneously. So if I solve equation 2 and equation 3 simultaneously, from equation 2, I'll have C1 to be equal to minus C2. If I call this equation 3 and I substitute equation 3 to, if I substitute equation 4 to 3, I will have minus, this is minus C1 here is minus C2. So I have minus C2 minus 2C2 equal to 4. Right, so minus minus is going to give me a plus. So this becomes C2 minus 2C2 equal to 4. All right. So this is C2 and this is minus C2. So C2 minus C2 will give me minus C2. So this will be equal to 4. So if I make C2 the subject formula, I'll have C2 to be equal to minus 4. So if I substitute the value of C2 to either of the equation, let me say equation 4. So substituting C2 into equation 4, I'm going to have, this is C1 equal to minus into minus 4. Alright, so C1 here becomes 4 as our answer. So I'm going to substitute the value of C1 and then I'm going to substitute the value of C2 to the auxiliary equation to get my particular solution. Alright, so from the auxiliary equation, I have this. Alright, so I will just substitute the value of C1 and then C2. So y becomes equal to, so the value of C1 here is 4. So I have my exponential minus x plus, so the value of C2 here becomes minus 4. So here turns to minus 4. Then exponential, I have minus 2x. Alright, so this becomes the particular solution of the problem and that becomes our answer.